Hello everyone, my name is Robert from SolidCAD. Thank you again for joining part 3 of our TruNest webinars. And Matt, he'll be doing the rest of the show here to take you through and end this series. And if you guys have any questions, if anybody out there has questions, please post them on the questions or the chat window, preferably on the questions window. And we'll try to answer them near the end, or if there's a chance in between things. So I'll hand it over to Matt now. Thank you.
Thanks, Rob. Welcome everybody. So today we've got our part 3 of the TruNest for Advanced Digital Manufacturing webinar series. Today we're going to be focusing on heavy plate fabrication. So a little agenda for today. We're going to be going over some digital workflows, looking at material optimization, ERP, MRP integration, the interface from TruNest to Inventor, leveraging some revision control via Vault, Autodesk Vault, managing our material inventory, tracking remnants throughout the cutting process as well, and then specifically for the heavy plate technology, we're going to look at multi-torch optimization, some Pierce and Lansing optimization, as well as plate marking, chain bridge cutting, some toolpath optimization, and skeleton cutting. So for those of you who don't know, my name is Matt Thorn. I'm the Senior Manager here at Magestic Technologies in charge of product and customer success. So I'll take you through a little bit about TruNest first. So TruNest is an advanced nesting and manufacturing software. Really our bread and butter is integration and automation. We leverage our database backend for TruNest to be able to integrate into business systems like ERP, MRP, and drive processes, providing lots of automation for repeatable tasks, things like that, all around the nesting and cutting process. We've been around since 1991 in various industries, including transportation, aerospace, construction, and power generation. A little bit about the materials. Generally, we can cut any material, specifically all kinds of metals, whether they're thick or thin, any kind of wood, composites, leather, foams, plastics, really any 2.5D cutting process. We can certainly support those kind of materials and machines that you have. So a little bit more about the machine tools. Today we're going to be focusing a bit more on the plasma cutting, but typically we support contour cutting and multi-tool cutting processes like lasers, water jets, plasmas, oxyfuels, punch presses, routers, and any combination machines, punch route, punch laser, things like that. We do write all the post processors for our machine tools within TruNest, so we can support any machine, new or old, and drive that for you in your shop. So let's take a look at the workflow for TruNest. So first thing that we have inside of TruNest, and we'll kind of take you through this through the webinar and a live session, but the first thing that we bring into TruNest is the CAD data. So whether that's native CAD data, specifically from tools like AutoCAD, Inventor, SolidWorks, things like that, we can support really any CAD data input. If you have generic data like DXFs or IGES files, DWG files, you can also support those into TruNest, as well as legacy NC data. So if you've got some cut files from the past that you want to transfer over, we can also bring those in and re-optimize those nests as well. Additionally, we can integrate with PLM or PDM system. In this case, we're going to be looking at Vault today, around the revision control and product life cycle for those parts as well. From there, once we get the parts in the system, We're going to process those, make our nests, and send those to the shop floor. So it doesn't matter what machine you're running these on, whether you have lasers, punches, plasmas, water jets in the shop. We can drive all those different machine tools and optimize the workflows for the parts for each of the particular tooling processes. And we do this by taking information from your orders and your inventory that's available and populating that all into TruNest as well. And all the results that we get, we generate all the reports you may need, turret reports to the machine tools, as well as efficiency and inventory reports as well from the nesting process. At a higher level, we can start to integrate ERP and MRPs, as well as automation to drive all these systems together and provide a suite of tools that allow you to automate this entire process from beginning to end. So from there, I'm going to switch it over to my demo. So I'll go ahead and switch this. So I have TruNest up here, and the first thing that comes up when I bring up TruNest is the authentication screen. And the reason we do this, we require username and password, is because we tailor the experience or the workflow for each user based on their login information. We can also track things that the user is doing within the software, parts that they're bringing in, nests that they're generating as well, just so we can understand what information is being created by which user. So if I log in here, since I belong to more than one workflow as an administrator, it's going to ask me to pick which workflow that I want to log into or which group. So I can log in as an admin, an engineer, or the shop floor in this particular setup. So I'll go ahead and log in as an admin for now. And that's going to give me access to a suite of tools up top here in the ribbon and a particular layout in the tree over here on the left. So we've tailored the experience for some of these tasks here, like inventory management and nesting default management, as well as scheduling orders, things that an administrator would be doing within the product. Over on the top right side, I've got a user profile tab that tells me who's currently logged in. So I always know what user that I'm logged in as. And if I belong to these additional groups, I can actually switch to the different workflows on the fly. So if we want to take a look at an engineer, we'll see the ribbon and the tree has updated to the primary tasks that are involved for the default engineer in this workflow. So by default, an engineer is responsible to bringing in CAD data, either from CAD files or from the PLM system, as well as maintain inventory and material constraints for nesting and make sure that all the materials within TruNest are aligned with all the materials on the design side. If I switch over to the shop, we can see some more of the downstream processes that the shop is responsible for in this particular workflow, which include entering order information, scheduling those orders, and creating the nests, generating the NC code, and sending that down to the machine. So we'll switch back to an administrator, and I'll take you through just the basic steps to go from end to end to the entire TruNest process. So it's really 3 steps. The first step being we need to bring in our geometry, and then we're going to create our orders, and then we're going to create and manage our nests. So under part import, I have a lot of different options here. The first one being parametrics. So if you have some parts that can be parametrically designed or driven, we can support some of those within TruNest as well. We have some default shapes in here just to kind of demonstrate. So you can drive rectangles, circles, squares, ring shapes, U shapes, things like that off of just inputting parameters within the system. And it will save you the time for these generic shapes to not have to draw those and bring those in separately. You can just create them on the fly as you need them. The next option here we have is translate. So translate is a geometry to geometry translation, meaning that any of the native CAD formats, generic CAD formats, or legacy formats that you have, we can bring those in and translate them into what we call TruNest geometry. The reason we do this translation process is at the same time we're attributing the geometry with manufacturing information that we understand about the particular equipment and the information within the geometry file itself. So we're bringing that across through this process. The next type of translation is an automatic translation. And this goes one step further from the actual translate process. And it starts to investigate the geometry file for what I like to call metadata information, which is information like bill of materials, any kind of etching information, marking information, information that is not necessarily geometry, but is important for us to carry along through the manufacturing process. We can also bring all that information in as well through this automatic step. So this is the step that I'm going to be using for some of the Inventor data that I want to bring into the system. And then one of the last part import options that I have here is the vault integration. So this is really a one-click integration to be able to bring stuff out of your vault system and into TruNest. So what I need to do is I just need to give Vault the assembly or the part files that I'm looking for, and it's going to go through and look through my Vault database. It's going to extract those locally to my particular computer. It's going to do that translation process, and then it's going to kind of remove those from my computer. And it does this in a way that it doesn't alter any of the revisions or versions within that Vault database. We're only checking out read-only versions of these parts for the sole purpose of bringing them into TruNest. So I'll go ahead and select my assembly. I'll click on the download parts, and I'm going to get the screen that asks me to log into Vault. So I can give it my credentials. I can pick the server that I want to log into and hit OK. And what it's going to do is it's going to go ahead and look into Vault. It's going to bring down locally all those files that are associated to that particular assembly. And if anything goes wrong in this process, it's going to give me a list of errors in this particular dialog box. In this case, I don't have any errors, so I can go ahead and move on. And it's going to go ahead and move on to that translation process. So what it's doing is it's opening up that particular assembly. It's looking at all the part files, and it's translating each one of those part files. So we can see here now we have our TruNest geometry. So we have the part file, and you can see that some of the shapes have been colorized. This is based off the tooling information that I have preset inside of my tool libraries that tell me how to attribute particular geometry. So if I want to attribute geometry in a certain way and apply certain manufacturing constraints to that, we can colorize and do that on the fly during this translation process. Additionally, you can see some of the metadata that I pulled out from this particular file. So the name of the assembly, as well as the name of the part, the material that it's on, as well as the material thickness. So all this information was pulled out from the bill of materials. We also have the quantity of parts within that assembly as well. So I can kind of thumb through some of the parts and make sure I have all the parts that I want for my particular assembly. If everything looks good, I can move on to the next process. So now that we've brought our parts into the system, I can go to the next step, which is order entry. And here I have a list of every part that I have in the system. And I want to set up my particular orders. So I'll go ahead and use these filters up top for assembly, subassembly, and part name to build that order. So I know my assembly name is going to be the sample assembly. So if I didn't remember, I can type in some particular letters there and use some of the autocomplete if I have something that's likely named or similarly named to the assembly that I'm looking for. After that, I can begin to fill out my order details. So things like quantity of that particular assembly. So in this case, we're going to be looking at some high volume logic here. So we'll go ahead and make 10 of this particular assembly. For the due date, I can go ahead and pick a date on the calendar, and this is going to be the date that I want to group like orders by. So if I'm scheduling production ahead of time or just in time, I can kind of pick the days that I want to start aggregating parts on like materials by. So I can pick a date there. Priority of this particular order or set of parts. So the priority influences the position of the parts on the nest. So the higher priority it is, the closer to the front of the plate or the plates for the nest those parts are. So if I have any particular parts that are, you know, just in time or I need them now, I can use the priority to influence those, get those cut first and onto the processes while not affecting my production. Next, we have the job order field. So I can manually fill this out. In an integrated solution, a lot of this information that I'm going through here would be inserted from some sort of integration with MRP or ERP systems like SAP. So I can drive these orders, the quantities, all these different parts from that integration as well, which is kind of where the job order field comes in. I can put whatever I want to in the job order fields to sync back these orders, the amount of materials that I'm running, the parts that I'm running back to my ERP MRP systems. So I'll go ahead and add these orders. And we'll see this queue start to build up here. And if I had more assemblies or more parts that I wanted to add to this, I could continue adding parts to this list. But for now, that's going to be good for me. So I'll move on to the next step, which is scheduling these parts. When I come over to schedule orders, it's going to group all those parts on like materials and give me the options for machine tools that I have available to produce those parts on that material as well. So for instance, I have two different material types here, mild steel and galvanized steel. The galvanized steel can be produced on a plasma or a water jet, and the mild steel can be produced on the plasma or the laser. In this case, I want to leverage the plasma, so I'm going to select the plasma machine in both those cases. And what this allows me to do is it allows me to optimize my orders for my capacity in the shop as well. So along with the machines and all the different materials, on each one of these I have an estimate for the amount of material as well as the amount of hours that it's going to take to produce these parts. Everything down here in this table is everything that's already in the system. So I can take a look at my different machine tools that I've already scheduled down here and take a look at how many hours are currently lined up for the plasma machine or the water jet or the laser, and see maybe it's better for me to pick the water jet for this particular material because there's less work already queued up for that machine. So it allows me to make these decisions and try to better plan for my capacity as I move through manufacturing. So I'll go ahead and select these two particular rows. It's going to be created under this group 13 and nest prefix N. So I'll go ahead and schedule those. It's going to move it from my unscheduled orders down to my scheduled orders. We can see here I have these two different materials or nests under group 13, and they're ready and waiting in this scheduled status, which means they're waiting for me to nest them. So now I go on to my next step, which is creating my nest. So I'll go in, I have that group 13, and I'll go in under create nest. You'll see both of the different materials here. I can click on one, both, whatever I'd like to do, and go ahead and choose nest. So I'll go ahead and just nest to this plate or this material. And what it's going to do is it's going to use all the different algorithms to decide what is the best plate size and efficiency for the amount of different inventories that I have. So you can see it was trying the 60 by 120, now it's trying the 96 by 48 in order to give me the best mix of plate sizes that I have available. It's also going to use any remnants that I have in the system at this time, if I do have any remnants, to give me the best material utilization for the material I have in the shop. This screen also gives you a look at the nesting efficiency. So it's a preview of the current efficiency for this particular nest run. After the nesting process completes, we're going to see some different optimizations run as well. So in this particular case, we are running a reduced piercing or minimum piercing logic for these particular nests. And what that optimizer does is it reduces the amount of times that we actually have to pierce through and do a full pierce cycle for the parts that I've created. And what this will do is it will leverage some of the kerf from previously cut parts in order to lighten up the pierce cycle to cut additional parts on the plate. So we're going from part to part on each one of those throughout the nest, and we'll kind of see that when we look at the results. Additionally, it's running another optimizer called sheet cutting during that process, which leverages processing of the sheet into smaller pieces, so it's easier for the operators to remove those from the machine bed as well. And lastly, during that step, it also runs the post-processor for each plate. So it's generating all the NC code with all the optimizations and toolpath optimizations I mentioned before, and getting that prepared to send it down to the machine. So I brought up my result here, and I can go through each of the plates and look at the different parts. So if you see each one of these lines, this is the reduced pierce logic. So what the reduced pierce logic does is it takes the lead-in from a shape, and it uses that lead-in to do a faster pierce cycle to cut the next shape out. And what this does is it reduces down to the amount of time it takes to pierce through the material and cut out all the shapes on that particular plate. So in this case, we're only ever doing that pierce cycle one time for the nest, that full pierce cycle. Additionally, you see these dotted lines underneath the nest. So this is the sheet cut optimization as well. And it's going through and it's dividing that sheet into smaller pieces in order to make that easier for the operators to remove. So we can go through each one of these particular results and take a look at the nesting results there. Okay, this one is it actually picked a remnant, I've got a remnant code here that it used. So it's using a remnant in order to, since it didn't need a full plate for the rest of these parts, it's using one of the remnants to gain efficiency for this particular plate. And then if it needs to generate a remnant as well, maybe it didn't have enough remnant pieces of material to nest the rest of these parts, it will generate its own remnant, and I can use that remnant back into my inventory once I'm done with this particular nest. So we've got this result. What I want to do now is I can actually modify some of these parameters on the fly. So under each material and each nest, I have a part list, a plate list, and nesting parameters. And this takes the default values from what we import and what we store in the system, and it allows me to modify it for this particular nest run only. So in this case, I want to take a look at some nesting parameters that I have. On this particular machine and this particular plasma that I have set up, I've actually said that this machine has 8 different heads available for me to use on during the nesting process. So in this case, I'm actually just going to use 4 of those heads by changing these parameters. So before I wasn't using any, I was just using the main torch. Now I'm going to use the main torch and 3 other torches as well for this particular run. And I'll go ahead and save that setting. We'll go ahead and launch this nest as well. So it's going to go through that same process. It's going to go through the nesting on each available piece of inventory, and it's going to optimize the position of the parts on the nest for this, what we call multi-torch logic. Now, even with the multi-torch logic turned on, it's going to optimize the parts on the plates in such a way that it still leverages all the sheet cutting as well as the reduced piercing logic that's being applied. So we'll just speed this process up a little bit, give it some time. And then if I want to just kill it, I can hit exit, and it's going to give me the result up to that point that I've generated. So there it's running, again, the minimum piercing logic and the sheet cut logic as well, and the post processor again. Okay, so I've got these parts. Let's take a look at the results. Okay, so now we're going to see some different colorization to these nests as well. So I'm going to take this shade by and go to shade by entity. And now we're going to see some different colorization here. So I said I have the 4 torches for this particular nest. So now we can see some of the results of the 4 torches. So all the different colors represent the different torches that are running. The blue color is the main torch, and then the green, light blue, and red are the essentially the other torches that follow the main torch. We can go through the entire process here, and you can see it's doing some torch reduction as well. So we automatically do the torch reduction process in these particular nests. So you can see some of these parts here and here are part of that torch reduction logic. So they're only done twice instead of 4 times like some of the other parts. So we're reducing from 4 torches down to 2 in this case. So we can take a look at some of the other results. Again, you can see some of the same logic that we're doing here for the multi-torch. And again, you'll get some results that are in somewhat strips across the plate, but that doesn't mean we won't do some torch reduction and part integration as well, if it's more efficient to do so. For example, like this one. So in this case, we've used all 4 torches, and at the end, we found we still had some room on the plate to fit some more parts, so we actually put them at the top of the plate, and we're going to reduce down to just that 1 torch and process these particular ones. So all the while, we're still doing the sheet cutting as well as the reduced pierce logic on all these parts as well. See if we've got some different results. Very similar result there. And then here you can see some of that as well. So in this case, we're going from 4 down to 2 in this case, and you can see some of the part integration here for the torch reduction. So these 2 parts are going down to 2 torches, and it's integrating with some of the space. So not everything is in this lane fashion, as we see in some of the results. If the parts are more efficient to lay out like this, we will. But if you have some more, parts that are, not as rectangular, we can also, the solution will also nest them in a fashion like this as well. So in this case, we're leveraging 4 of the particular torches, but like I said, on this machine, we have actually 8 torches. So what I can set up the nesting system to do is I can set it up to nest in stacks. So that's what I'm going to do next. So I'm not leveraging the full capabilities of this machine yet. So I'll go back to my nesting parameters, and I'll run this one more time. And this time I'm going to give it a stack of 2. So this means I'm going to have 2 plates next to each other on the machine bed. If the machine bed supports it, in this case it does, it's going to give me everything in a quantity of 2. We're going to see the number of plates be reduced and the quantity of each plate be increased as well. So I'll go ahead and save my change there and run this one again. And just for the sake of time, we'll go ahead and speed some of these up. So let's take a look at our results now. So now I've actually forced a quantity of 2 up here. So now I'm producing 2 of this exact sheet when I'm producing this sheet in an effort to leverage all the 8 torches that I have here. So the nesting results look very similar to the what they were before, but now in this case, we can put those sheets side by side and leverage all the torches that we have available on this machine. So again, you can see the result there. We're using a remnant piece of material in this case, again with a quantity of 2. If we have 2 of those remnants, we can use that remnant in this logic as well. In this case, we do. Again, leveraging that quantity of 2, even with a torch reduction as well. And again, here we have some torch reductions, our quantity of 2, all in the same nest. So down here in the report as well, you can see the spacings of the torch for each of the torches as well. So if you wanted to, you can directly print this particular page, as well as we'll go on to the next step. If I'm happy with these results, the next step that I want to do is send them down to the machine. So I can do that directly by going to Manage Nests. These are all the plates that I have currently nested. You can see the ones that I've nested with a stack of 2 have that quantity of 2. So what I can do is that if these are ready, I can send them down to the machine. That's going to send any remnants back into inventory to be used the next time that I have nests on that same material. It's also going to change the status. So this status has been tracked for this order and these particular parts and plates throughout the entire process. And it really tells the system at what stage things are in for the user as well. From here, I have a lot of other different options available to me. I can do things like automatically create a PDF of the nest. Again, if I wanted a printout or a PDF of that nest, I can generate it on the fly to be able to leverage in, if I had travelers or if I want to store that document electronically and give it to the shop or something like that, I can certainly do those things. I can review the NC code. So if I wanted to, I can click on a particular sheet and it's going to give me all the different NC code. I can review that here, make sure everything looks okay. If I didn't want to comb through the NC code, I wanted more of a graphical view, I can actually click on the backplot, and the backplot's going to show me the result that I have for reinterpretation of that NC code into a backplot. And notice here the backplot looks a little empty. And in this case, we're showing you the NC code for the main torch. So everything else gets cut with the other torches in this case. So you'll see a lot of, you'll see the main torch showing you some of the geometry that it's cutting, but it's also cutting everything else on the plate. Additionally, you see some of the lines for the sheet cutting to divide that up in the sheet as well. So on these particular parts, you'll see that there's custom lead-ins. So we do what's called a question mark lead-in on some of the internal holes. And we find that this technology is actually really nice to improve some of the quality of internal holes and things on the plasma machine. We also support things like TruHole or advanced hole technology on certain machine tools like hypertherms and things like that. If that's the kind of machine that you have, you can also support their respective technology to drive some of the internal hole cutting on their machines as well. You'll also see some of the reduced pierce logic. So you can see we tag on this particular lead-in, come out here, do our piercing out here, cut the shape, and then we use that place that we already pierced through the part to go into the next shape. And we do this in a way where we're always going towards the skeleton or towards where more of the plate is available. So we're always cutting into what we call the meat of the plate. And that's so that we make sure none of the parts, the quality of the parts are sacrificed when we're cutting these out. If this happened to be on the other side, this part could end up snapping back or just because of due to the internal stresses, the material, things like that, and end up getting ruined just from having this lead on the other side of the particular piece of geometry. So we're automatically doing these optimizations to keep that in mind. And you can kind of see some of that here as well, where we're picking the back of the part in order to make sure that none of these parts end up snapping back and damaging the part or any of the equipment. Okay. So when we send that, the NC code is now in the shop's hands to be run on the machine. If we take a look at our inventory, we can see on that piece of material, we've got our remnant code here that we sent back as well. So we sent back a quantity of 2 of this particular remnant back into our inventory to be used next time that we leverage this material. TruNest also has efficiency reports and nesting reports to give you an idea of all the different settings and costings and part cost, material costs for each of the plates and parts as well. So we can scroll through here and see all the different settings that I used on the particular material that I'm running. So we can go through, we can see the number of stacks that I used, as well as the number of heads that I used, number of torches that I used for this particular nest run, all the different parts, all the part data that was automatically taken in from Inventor is all leveraged here. Any of the grain constraints that were applied to those parts in the design software are leveraged here as well. We can see all the different quantities for those parts as well. The different materials that were used. So we had two remnants of this particular type that we used, as well as 2 different stock sheet sizes, 120 by 60 and 96 by 48. We can look at the nesting efficiencies for each one of the plates, as well as things like total nested cost and single sheet nested cost. You can also see the different costs of each part based on the costing values that were set up in some of the defaults for the software. So a couple different things that I didn't show with these parts that I wanted to kind of show off, and then I'll open it up for questions. So let me jump back to my PowerPoint presentation. So in this case, what I showed was the reduced piercing logic or minimum piercing logic, which still does that kind of enhanced piercing cycle for each part. We do also have optimization technology that will chain or bridge parts together in order to keep the torch on and reduce, essentially it also reduces the amount of times that we need to pierce. Some of the things about this process though, and in particular you're seeing a chain cutting process here, it will chain parts together in part groupings. So you can see the little different groupings that we have here to chain those together. And we use the space between parts in order to drive the machine around specific geometry and start to cut out some of these shapes. And while this keeps the machine on, it also makes the material utilization less efficient. So we have to have the space in between parts in order to place these chains between parts in order to drive this optimization process. So depending on your constraints and your manufacturing concerns, chain and bridge cutting can be effective, but a lot of our customers end up using some more of the minimum pierce logic as well. So it's a good example of chain cutting for this particular machine, and bridge cutting as well. So up top here we have chain cutting, which kind of gives you an example. So if we're starting over here and going around the shape, we kind of build this nice little chain around each one of these parts and kind of come up with a part grouping. And what's nice about the chain cutting versus the bridge cutting is that each part is cut out before the next part. In a scenario like here is what's called a bridge cut, and we make a small bridge between each part. And this allows us to gain material utilization and nest parts closer together, but any of the bridges between parts, essentially you're combining 3 parts into one. So if this part ends up tipping up, or somehow the quality is sacrificed, you've sacrificed 3 parts instead of 1. So it really depends on the processes that you use in your shop, which methods and which optimizations that would work well for you. But we do support all of these different types. And then lastly, if your machine has the capability to bevel as well, we support beveling from your CAD solution as well. So what we do is we attribute some of the edges with the different bevel types, whether it's a K bevel or just a standard angle bevel with a land, things like that. We'll attribute each of the edges that have these different types of bevels, and that'll go through the entire nesting process and down through the NC code. So we also do some different optimization for the cutting on the bevels as well. So we'll do some kind of quarter cutting optimization for some of the bevels as well. In this case, where we'll kind of lead out of the shape, do a loop and then come back this way. And we'll program that toolpath optimization automatically for you. So all you would need to do is really just design the parts as is, and we would attribute all the bevel information automatically. So if you do have that process or that capability on your machine, we can certainly support that as well. So I will open it up for questions.
Okay, Matt. Got one question.
Perfect.
Can you manually edit the NC code in the NC reviewer?
That is a good question. So in the NC review itself, it's really what it says. It's for review. So you can search through the NC code and find specific G&M codes that you're looking for, specific breakpoints, things like that. But if you wanted to edit it, what we do is we just bring up a text editor for you to edit that NC code. So you can do that right in a standard text editor, and we can wire an edit function that would do that for you.
Okay, we got one more. Let's see. Is it possible to add etching within TruNest, or would it need to be added in metadata?
That's a good question. So let me switch back off my presentation real quick and just kind of show off in Nest. So I think I have some other examples here. So all the information that we have inside of TruNest is at our fingertips. So some of the metadata, as I call it, from Inventor that we bring in, all that information ends up being populated in one of these 3 areas, either in the part parameters, the material parameters for the plate, or the material parameters for nesting. So we can see some of the part information that comes along here, as well as there's comment fields where additional information that's outside of this can also be leveraged. And we can make label information on the fly or etching data on the fly from any of the data that we have in the system. So if we wanted to etch in the part name, things like that, we can certainly do that for you on the fly. You can also provide that data as well from the design. So if you wanted to place a label that you wanted us to carry through and nest, we can also do that. Let me see if I have some other examples here. So here you can see things like parts that need to be bent. We can carry through, in this particular case, some bend line information, and we can etch that on the part as well. So whether it's just manufacturing information or part information, we can certainly carry those things through. Trying to see if we have one with labels on it. Give me a second here. But essentially, we can do either or for you. Some more bend information on this one there. So we can automatically generate the labels, which is typically better than providing a label location, because if we nest something at a certain orientation, your label's going to follow that orientation as well. So if we automatically put the labels on, we'll make sure that they're always at the same orientation or the best orientation to fit on that part without overlapping other features and things like that. So hopefully that answers your question.
We've got another one.
Sure.
Does TruNest only work for through cuts, or does it have the capability for blind feature cutting?
That's a good one. So what I'm going to guess is that there's certain things, to me, a blind feature is something that isn't necessarily on the face or is on one side of the part versus another. So potentially things like a pocket or maybe drill holes that don't go all the way through the part, things like that. So in those cases, we can certainly support those geometries. We can bring in those shapes at the particular depths that they are, and we'll drive things like router machines and other types of machines that may support that type of geometry. Some plasma machines have different heads on them for drilling and other operations as well. So we can certainly support blind holes and pockets and things like that. We can also support special tools. So if you're doing a special process where, you know, for instance, on a router, sometimes you have what's called like an auger bit, or which will kind of mill out the middle of a shape or in the thickness of the shape that's not necessarily a feature on either side, but something in the middle. This is really common in like sandwich panels and things like that for aerospace. So we can also drive special tools that have these processes as well. It's really about, you know, understanding the geometry file and attributing those accordingly for your manufacturing process.
Yeah, that's the only questions we have right now.
Okay. So we'll leave it open for some more questions. I'll go on to kind of my last slide here. If I didn't answer your question, go ahead and you can always reach out to myself or Rob if you have some more questions at any time. Both of our emails here as well as the websites. Feel free to reach out. I'm happy to answer any additional questions that anyone has. You know, if there wasn't.
Matt, I have a question myself on the case of the etching. Can you do custom etching in a way to do barcodes or QR codes or something like that? That kind of imagery?
Yeah, that's a great question. So we can certainly support any QR codes, barcodes for etching as well. So we'll automatically either create that barcode on the fly based on, you know, the text information that you want to convert into that barcode or QR code, and kind of be able to etch that on the parts for the machine. Some machines actually will do some of the conversion on the fly, and we can certainly support that as well. So I know some laser machines like Trump are starting to support QR codes on kind of support their own QR codes for parts and things like that. So whether the machine can do it or we generate that, we can certainly support that type of information.
Awesome. Yeah, that's it.
Okay. Great. So again, you know, if there's any other questions after we close it out here, please reach out to either myself or Rob, and we'd be happy to answer those for you.
Very good. Thanks again for your time, Matt. Great job again. And look forward to future webinars together.
Sounds great. Thanks everybody for attending today.